back to the deep dive, where we unpack fascinating ideas, uncover some surprising connections, really just for you. Today we're diving into a story that I think just perfectly shows the beauty and wealthy interconnectedness of mathematics. It's about a problem that stumped the brightest minds for decades. We're talking about the Basel Problem, and how a young Leonhard Euler, with this incredible stroke of genius, found a way to link things that seemed totally separate. Things like trigonometry, complex numbers, infinite series.
Yeah, it's amazing how he brought those together.
Right, he didn't just solve it. He showed this stunning, almost like magical connection involving Paley.
Pi squared, of all things.
Exactly. So the core question Euler tackled sounds simple enough. What's the sum of the reciprocals of the squares of all positive integers? 11 plus 12 binaries plus 13 bar g plus 14 area. Just keeps going infinitely.
It seems like it should just add up to something, but what?
Yeah, you'd think it would trail off. But the answer, which we're about to unpack, is this incredibly elegant number involving...
It really is a testament to finding order in apparent chaos.
Totally. Okay, so let's get into this incredible proof, step by surprising step.
It's really remarkable how Euler managed it, weaving together these distinct mathematical fields. His solution, it's not just about the answer, right? It's more a profound statement about the unity underneath it all.
Absolutely. It shows how problems that seem totally isolated can actually be, well, deeply connected. And to really appreciate this deep dive into the Basel problem, we need to start with what many call one of the most beautiful equations ever.
Yeah, yes, the jewel.
Euler's formula, x equals cosx plus isinx. For you listening, if you haven't seen this before, what makes this equation so, I guess, revolutionary? Why is it our starting point?
Well, the sheer audacity of it, really. You've got e, the base of natural logarithms, usually tied to growth. You've got e, the imaginary unit, square root of -1. And then you have cosine and sine, these wave-like periodic trig functions.
Completely different worlds, seemingly.
Exactly. And Euler just says, bam, they're connected like this. He saw that the continuous dynamics of growth captured by e could perfectly map onto the cycles of waves using imaginary numbers as the key.
Wow.
It's a fundamental bridge. It tells us any complex exponential can be broken down into a real part, the cosine wave, and an imaginary part, the sine wave. The implication is huge. These aren't just related, they're like different faces of the same mathematical object.
Different faces of the same structure. I like that. So Euler has this amazing identity, this bridge, but he didn't just stop there, did he?
No, that was just the beginning.
So what was his next brilliant move? How did he start to sort of dissect these functions even further?
Well, his next step was, again, quite brilliant. Instead of just looking at x as a whole, he decided to expand it, express it as an infinite power series, like an infinitely long polynomial.
Okay.
So x becomes 1 plus 9 by 1, plus 922, plus 933, plus 944. Just keeps going forever.
Right, the standard Taylor series expansion.
Exactly. Now, here's the really neat part. You meticulously separate this infinite series. You gather all the terms that don't have an I, the real parts, and what pops out. The infinite series for cosine, cosx equals 1 by sota 2, plus x or 4.
Wow, okay.
Then you collect all the terms that do have that I attached, the imaginary parts.
And that must be sine.
Precisely. You get I times the series for sine, sinx equals x3 plus xx5.
So he's basically turned these smooth, wavy functions into algebraic lists of terms.
That's a great way to put it, infinite polynomials. And that opens up all sorts of analytical tools, because now you can kind of treat them using polynomial algebra, even though they're infinite.
That's powerful.
And for our journey today, we need to focus on a slight twist on that sine series. So we just divide the whole sinx series by x.
Okay.
We get sinx x of 1 by Selvo 3 plus xx5. Let's hang on to that one. Call it our first key expression. It's crucial.
Got it. Expression 1. The power series for sinx x. So he's turned these continuous functions into these, almost countable infinite polynomials. Now, here's where I think it gets really audacious, maybe a bit unconventional for the time.
Definitely unconventional.
Euler then looked at the roots, the zeros of the sine function, which, we usually think about for simple finite polynomials. So what does it mean for sinx to be 0? And how on earth did Euler use that knowledge?
Right, so sinx equals 0 whenever x is an integer multiple of phi. 0, phi, neckle 2, neckle 3, neckle 3. Forever in both directions.
Okay, the places where the sine wave crosses the x-axis.
Exactly, but since we're actually looking at sinx x, that x0 root gets kind of canceled out by the division. It stops us dividing by 0 there.
Clever.
So for sinx, the roots we care about are the non-zero ones, pi, 5, 2, 3, and so on.
Okay.
Now think about a normal polynomial. If you know its roots, say r1, r2, r3, you can write the polynomial as like c xr1, xr2, xr3, some constant c times factors based on the roots.
Right, standard algebra.
Euler then made this incredible leap. He thought, what if I treat this infinite series sinx like an infinite polynomial?
Whoa.
And he said, okay, if it's like an infinite polynomial, maybe I can write it as an infinite product based on its roots.
So an infinite
It's
multiplication.
an infinite multiplication, yeah.
Yeah.
Based on all those roots. Sinx, 2, 3, and so on.
How's that look?
It led him to this factorization. Sinx always is 1 by 4, 1 by 4, 3. It just keeps going.
Okay, wait. Where do those 1x something terms come from? I thought it was x root.
Good question. So you could think of x and x plus w for the first pair of roots, but for symmetry, and to make things work out nicely, especially since we started with sinx, which is 1 at x plus 0, he used pairs like 1xi and 1 plus x.
Right, okay.
And when you multiply those two together, 1x, 1 plus s, what do you get?
Difference of squares. 1x up, so 1x up.
Exactly. And he did that for every pair of roots.
Yeah.
2 gives you 1x2, which is 1 by 4 quarters.
And 3 gives 1 by 9 vol. I see the pattern.
You got it. It was a truly bold, maybe even slightly questionable step mathematically at the time, but his intuition was just unparalleled. Treating an infinite series like this, it was groundbreaking.
It really feels like playing with infinity in a whole new way.
Yeah.
So incredible. Now we have two totally different ways to write sinx.
Both valid representations of the same function.
One is that power series.
Yeah.
1 by 3, 3 plus x Julie 5.
Our expression 1.
And the other is this wild infinite product based on the roots. 1x prof, 1 by 4 prof, parts prof.
Our expression 2.
So how did he do it? What was the final connection, the aha moment that links these two things and solves the Basel problem?
The genius here is actually based on a pretty fundamental idea. If you have two polynomials, or in this case, two infinite series, that represent the exact same function.
They have to be equal term by term.
Precisely. Their coefficients for each corresponding power of x must be identical. So Euler focused on the exon term, just the x were apart. Let's look at expression 1 first, the power series. 1 by 3, 5, plus xo(5). What's the coefficient multiplying xoers there?
It's right there. -1 on 3.
Exactly. Medicine 16, since 3 is 3, 2, 1, equals 6. Keep that negative 16 in mind.
Okay, negative 16.
Now the tricky part. Look at the infinite product. 1 by 4, 4, 1 by 9. How do we find the XOR term here?
You have to imagine multiplying it all out. That seems impossible.
Sort of, but you only need to think about how an XOR term could possibly be formed. To get just XOR, you have to pick the XO apart from exactly one of the brackets.
I see.
And then you have to pick the 1 from all the other infinite brackets.
Okay, so if I pick negative from the first bracket.
Then you multiply it by 1 from the second bracket, 1 from the third, 1 from the fourth, and so on forever. That gives you one contribution to the XOA term. XOA5.
And if I pick the XF term from the second bracket instead.
Then you pick 1 from the first bracket, negative 4, 5 from the second, and 1 from all the rest. That gives you negative 4.
And annex x9 from the third, and so on.
Exactly. So the total coefficient of the xot term in this infinite product is the sum of all those individual coefficients. Negative 1 by 14, 19 10.
Wow. Okay, that makes sense. You're just adding up all the ways to get exactly xot.
Precisely. You can't pick xot from two brackets because that would give you xot, which we're ignoring.
Right, so now we have the xot coefficient from both expressions.
We do. From the power series, it was matig of 16. From the infinite product, it's matig of 1 by 4, 19 6 quart.
And since the expressions are equal,
their xot coefficients must be equal. So, natig of 16 equals matig of 1 of 14, 19 third.
We're almost there. Look at the right side.
Yep, you can factor out matig of 1, 4 from every term on the right.
So natig is 16, natig I natig 1 times.
Yeah.
11 by amatigration plus 13 natig 1.
And that is the Basel sum we were looking for. It just popped out.
Amazing. So what's the last step?
Just a little algebra. Multiply both sides by matig bad. The negatives cancel out.
You get by 6 and 11.
Equals 11, 11 plus 12 others plus 13, 1 plus
there it is. By 7.
6. Absolutely stunning. If you connect this to the bigger picture, this was just mind-blowing back then. It took this sum, purely arithmetic, these fractions of integers.
Yeah, something that feels like it should be rational, maybe.
Right. And it links it directly, unequivocally, this fundamental constant from geometry, from circles. It showed this deep, deep connection between number theory and geometry that nobody had really seen so clearly before.
Like finding a hidden tunnel between two different castles.
That's a perfect analogy. It was truly groundbreaking.
Wow. So we've just walked through, a masterpiece of mathematics. mathematical deduction. We went from complex exponentials
Euler's formula.
through infinite series, these power series extensions, then that incredibly clever leap using the roots of sine, treating it like an infinite polynomial.
The infinite product.
And finally just comparing the coefficients, the excess terms, leading us straight to the answer. The sum of the reciprocals of all positive squares is exactly f6. Elegant, beautiful, and just. Totally unexpected. A bridge between adding numbers and the geometry of circles.
Couldn't say it better myself.
So what does this mean for you listening? Well, Euler's proof isn't just some dusty historical thing. It's really a testament to how deep understanding in one area can just crack open secrets in another.
The power of analogy and intuition.
Yeah, it's about the sheer ingenuity. Seeing harmony and order where others just saw an endless list of fractions. It really highlights the beauty of these connections.
It really makes you wonder, doesn't it? This deep dive into Euler's thinking.
Yeah.
It raises that question, how many other problems out there in math, in science, anywhere that seem totally unrelated? How many might be connected by some elegant, unexpected link like this, just waiting for someone to find it?
That's a great thought. What hidden connections are still out there?
It definitely inspires you to look beyond the surface.